Hi, I'm Toru Tanzawa. Let's consider the power loss in charge pump together. This is a charge pump circuit, which is composed of multiple capacitors and multiple diodes connected in series between the input to output. And then we have the N capacitors and plus one diodes here. Arrows in red indicate the input, the power flow from the input side, and the arrow in blue indicate the output power. So using this test condition, you can design the charge pump. Then you can draw this kind of graph showing the power conversion efficiency versus over the output voltage. The question is why does PCE look like this? So this is the theme of this the discussion. Okay, we have the n pass through n capacitors and one pass from the beam, the total n plus one path. So to provide the average output current of IO to output voltage VO, you must provide the same amount of current to the last capacitor here, and also because you lost the same amount of charge as IO during a half cycle, you must provide the second last capacitor with the same amount of the charge. In this way, so these arrows equivalent, and therefore average input current is proportional to IO, whose proportional coefficient is n plus 1. This is the definition of power conversion efficiency: output power divided by input power. And you can input this equation into here, then IO is cancelled out. And if you define the VO max as this means that the VO can go as high as VO max. And using this VO max, then PCE can be expressed by this equation. And this equation shows like this, the red line, which has the straight line, and the PC can be 1 when VO is VO max. However, at this point, the output current IO is 0, and therefore it's even though mathematically this is they indicate the PCE equal 1, but it's not the meaningless in practice. And usually you need to design the charge pump to output current at of course certain amount of current at the target output voltage here. So at this point, your PCE should be below 1. How the PCE is reduced from 1 depends on how far from your operating point from VO max. So you want to increase the PC, or to get the high PC, you need to design the charge pump with the very minimum N, meaning so this point should be close to your operating point like this. However, in this case, the IV curve should have the very much steeper than before. So to do this, your output, the impedance of RO must be very low. So this can be realized using a very large capacitor or very high operation frequency to get the low RO. So this is a kind of the PC versus area trade-off. Let's look at this in more detail in the next slide. Okay, let's consider the next neighbor two capacitors here. The before charge transfer, the first capacitor charged and the second capacitor of course charged up. However, the voltage at the second capacitor is lower than the voltage of the first capacitor to transfer the charge from the first one to the second one. And this the graph shows the voltage and energy stored in each capacitor. So because V1 is greater than V2, of course, stored energy is also the E1 is greater than E2. However, this difference is greater than this because the energy is basically proportional to voltage squared. After the switching on, the path from the first capacitor to second capacitor, the charge transferred until both the voltage is equalized like this. For simplicity, I assume that those two capacitors are the same size. Therefore, the equalized potential is the middle of V1 and V2 like this. And of course, the stored energy is also same between the two capacitors. And the thing is, the total energy before charging transfer and the total energy after charge transfer, if you compare those two, this energy after charge transfer must be smaller than the first one. So let's define the energy loss by the difference between the energy stored before and after charge transfer like this. You can simply calculate to be this number using the delta V defined by this. So this is related to the delta Q, the transferred amount of charges here. So using delta V, E loss can be expressed by this equation. Power loss is expressed by this, where the F is frequency of the charge pump. And then we want to reduce the power loss as much as possible, while we need to maintain output current of this value, because this C delta V is delta Q times F indicate average current from the left to the right capacitors. This is the same as the output current under the steady state condition. And the P loss here can be expressed by this, using IO instead of delta V, by inputting delta V to P loss here. And we know the output impedance of the charge pump is expressed by 1 over Fc. And so at this point, the power loss, intrinsic power loss, is given by RI squared, conduction loss. So to reduce the power loss, you need to increase F or C, or both. So this is the same the observation in the previous slide, like this. So to reduce the RO, you need to increase the F or C. So with this uplate, your the power conversion efficiency can be increased while the output current is maintained. Okay, let's look at the another contributor to P loss. This is the charge pump capacitor C, and if you want to realize this capacitor in the integrated circuit, you may have the gate capacitance of transistors, or MIM capacitor here, or MOM capacitor, using a multiple the metal wiring layers like this. And depending on the capacitor structure, the bottom plate plastic capacitance CP must exist in any case. For the N-well capacitor here, you get the very high capacitance density, however relatively large bottom plate capacitance due to the N-well to P substrate PM junction capacitance, and nominally the plastic capacitance ratio to the boosting capacitor C is about 3 to 10%. MIM capacitor is nominally fabricated using the top two metal layers, meaning the bottom plate has the very far placed far from the substrate or gate. Or similarly, the MOM capacitor has the smaller plastic capacitor, however, the capacitor ratio is about 1 to 2%. Because this node T1 is driven to 0 to V per cycle, and so this must be considered into the power loss. So additional input current can be calculated by this equation, because the CPB is the charge per capacitor times N, the total amount of charge, and we run the clock with the frequency of F. So the average input current is estimated by this equation. So now we have the equation. The total input power is composed of output power and intrinsic power loss and conduction loss and switching loss, like this. You can divide this equation by P. Then we get this the equation. The first term is the power conversion efficiency, and let's call the second and third term as IR square and FCV square. So the total three terms summed up to 1 always. So using this condition, you can estimate each component like this. So this orange curve shows the PCE. Why this the PCE is very low when the VO is very low? Because the IR square is major. And why the PC goes to 0 at the VO max? Because the output current reduced significantly, while this FCV square term has no VO dependence, like a constant in terms of VO. And therefore that ratio here increase very suddenly, and therefore the power conversion efficiency the collapse to 0. As a result, the PC has concave up the curve like this, and you can you are aware of the high PCE range is very narrow. Okay, let's review the FCV square on PC. When the FCV square is negligibly small, and we only have the intrinsic power loss like this, then PC has the straight line between the origin to the 1 at VO max like this. So with this curve plus the FCV square, then this portion is significantly affected by CV square term like this. Actually, the charge transfer has the certain amount of current ripple like this. So this is a voltage waveform between the two adjacent capacitors. This is the first capacitor discharged to the second capacitor, and second capacitor voltage increase like this. So when the actual switching current like this, the triangle case, then I squared has the very sharp shape than the case when the charge transfer is about a constant current like this. So this is the case when the clock frequency is very low, or the boosting capacitor is very small. Then the charge transfer affect the significant voltage change per cycle. or in other words, the transfer, the current from the one capacitor to the second capacitor has this the very high height. So compared to this, the extreme case where the switching current is constant, the RMS current is 33% higher than minimal case. So to realize this current waveform with no or negligibly small ripple current, you may need to run the charge pump with very high frequency. However, this affects high frequency makes the FCB square term increase, or you need to increase the capacity. So even though you transfer some amount of charge, but the voltage change at the capacitor is not so significant, resulting in the constant current. Or to flow the constant current, you may add the inductors between the two capacitors. So let's look at the how significant this current ripple on the PCE in the next slide. So we have two cases. The only difference is the term of a proportional coefficient of RO IO squared, 1 or 1.33. So you can draw the line like this, and this the blue line has the current ripple, include current ripple, which affects the mostly this region. However, the peak point is also affected. In conclusion, the PC of charge pump, why does the PC look like this? Because the charge pump has the intrinsic PC like this, because the lower VO range, the conduction loss, the contributor to very significant reduction in PCE. In addition to that, in a high VO range, the switching loss due to the plastic capacitance element reduce the PCE, resulting in concave shape like this. Okay, that's it. Thank you.